Welcome to today's video. We have so far found theorems that characterize the optima of multivariate functions, and today we are going to use those theorems to treat a few examples to show you how this is actually applied in practice. So today's video will consist of a couple of examples. We'll start with a function defined on R2, maps to R. And it's defined of f of x1, x2 equals 2 minus x1 minus 1 squared minus x2 minus 1 squared. I'm first going to show you a plot to give you an idea of how that function looks like. So here's a plot of that function. And you can hopefully guess there might be a local maximum in here. And let's see if we can find that computationally as well. Okay, so you remember our first order condition. We first need to find all stationary points. Those are the candidates for local maxima and minima. So let's find the stationary points. And of course that means we have to compute the gradient. Now the gradient of f, if we differentiate with respect to x1, then we get minus 2 x1 minus 1. And if we differentiate with respect to x2, then we get minus 2 x2 minus 1. So that is minus 2x1 plus 2 and minus 2x2 plus 2. And if you want that to be 0, then of course that means, well, x1 has to be 1 and x2 has to be 1. So our only stationary point is the point 1, 1. So we have one and only one candidate for a local optimum here. Next we classify that. So we want to find out whether this is a saddle point or a local minimum or a local maximum. So we need to have a look at the Hessian at the point x star. So the Hessian at 1, 1. First let's compute the general Hessian. We look back at the gradient here, this one. We need to differentiate that once more. So if we differentiate the first line with respect to x1, then we get minus 2. If you differentiate with respect to x2, then we get 0. We already know the Hessian of a continuously differentiable function is symmetric, so there will be a 0 here as well. And differentiating this line here with respect to x2 again yields a minus 2. Okay, so this is a pretty simple diagonal matrix that is constant, doesn't involve any x, so HF of 1, 1 obviously is that same matrix. So we need to find out whether this is a positive or a negative definite matrix. So let's have a look at the expression some vector v transposed HF of 1, 1 times the same vector v. Now that is v1, v2 transposed minus 2, 0, 0, minus 2 times v1, v2. And if we compute that, we get the following expression, v1, v2 transposed times, and this is minus 2 v1 minus 2 v2. And if you compute that scalar product, we get minus 2 v1 squared minus 2 v2 squared. And now if v is not the zero vector, then of course this is strictly negative for all v in R to the n, with the exception of the zero vector. So the matrix H f of 1, 1, the Hessian at that point in question, is negatively finite. HF of 1, 1 is negatively finite. And of course what that means is, by the theorems that you will hopefully remember, is we have a local maximizer. So x star equals 1, 1 is a local maximizer of f. And I'll show you the plot once more so that you can verify this actually looks right. Okay, let's move on to the second example, B. Again, let's take a function defined on R squared, mapping to the reals. We'll again use something quadratic, but now we include a mixed term as well. So the function we look at now is defined as 1 minus x1 squared minus x2 squared plus 3x1 x2. And let's first see what we can find out about that function before looking at the plot. Again, we start with stationary points. So we need to compute the gradient. Differentiating with respect to x1 yields minus 2x1 plus 3x2. And differentiation with respect to x2 yields minus 2x2 plus 3x1. We could also express that as minus 2, 3, and 3 minus 2 times the vector x1, x2, and we want that to be 0. Now that's going to be 0. We have to solve the equation system here for x1 and x2. So we'll do just that. Solve system of linear equations with that matrix here, minus 2, 3, 3 minus 2. What we need to do is we'll take this element here as our first pivot element. And then we just add 3 over 2 times the first row to the second. And that'll give an unchanged first line, of course, and the second line becomes 0 here. And here we get 3 times 3 over 2, that's 9 over 2, minus 2. Minus 2 is minus 4 over 2, so 9 over 2 minus 4 over 2, that's 5 over 2. So this is the matrix that we get after this first Gaussian elimination step. And that means we can solve for x star. This thing has obviously full rank, so the only possible solution x star is 0, 0. Okay, so we get this as the unique stationary point. That's the only stationary point here. As for the classification, we'll again have to compute the Hessian first. Remember the gradient looked like this here. And if we differentiate that with respect to x1 and x2 in turn, if we differentiate the first line with respect to x1, we get a minus 2. With respect to x2, we get a 3. And similarly, if we differentiate the second line with respect to x1, we get a 3. And differentiation with respect to x2 yields a -2. So that's just the very same matrix here. Now, is this positive or negative definite? Or maybe indefinite? Let's see. So let's again try to compute V transpose HF at 0, 0. Formally, we only need to check the matrix at this unique stationary point here. But of course, the matrix is constant, so that doesn't make a difference. So let's see, V1, V2, transposed -2, 3, 3 -2, and then V1, V2. So that yields -2 V1 plus 3 V2 in the first step, and here we have 3 V1 minus 2 V2. And so what we get is -2 V1 squared plus 3 V1 V2 plus 3 V1 V2 minus 2 V2 squared. So we have -2 V1 squared minus 2 V2 squared plus 6 times V1 V2, that mixed term here. Okay, so we have, on the one hand, we have negatives here. On the other hand, we have this mixed term that we can probably steer in every direction that we want. So let's see if we can find vectors where this value is positive and others where this value is negative. And that would prove that the matrix is indefinite. Let's start with a simple example first. Let's check the vector 1, 0. So 1, 0 transposed HF of 0, 0 times 1, 0. That means V2 is 0, V1 is 1, so we get -2 minus 0 plus 0. That's obviously negative. Now, can we also get a positive expression? And the answer is yeah, probably yes, if we just lay enough weight on this part here. So for example, if we use a vector 1, 1. Now what happens is we get, again, -2 and a -2 for the V2 part. And then we get 6 times 1, 1. So plus 6. So that's 2, and that's obviously positive. Okay, so it turns out there are vectors where this product V transpose times the Hessian times V is positive. There are vectors where this is negative. So the matrix is indefinite. HF at 0, 0 is indefinite. And that means the point 0, 0 is actually a saddle point of the function f. Okay, and to see that this is actually true, here's the plot of that function f. You can convince yourselves that it looks like a saddle point at the origin. Okay, one final example, part C. Let's take another function defined on R squared to R, defined simply as x1 times x2. So we just take that mixed part and see if that makes any sense here. Again, we go for the stationary points first. The gradient of f is simply x2, x1. Well, this is 0 if and only if both values are 0. So again, the origin is our unique stationary point here. For the classification, we need to compute HF, the Hessian, the general Hessian. So first we take the derivatives of the first row of the gradient with respect to x1, that's 0. With respect to x2 we get a 1. And for the second row it's 1 with respect to x1 and 0 with respect to x2. So that is again a constant Hessian. So that means we can again investigate this expression here. And that is v1, v2 transposed 0, 1, 1, 0, v1, v2. So we get v1, v2 transposed times v2, v1. So in effect we have 2 v1, v2. And while this does look like a nice positive expression, it actually isn't, because of course the v's can also contain negative entries. So in this case, if both of them are positive, for example, like this here, 1, 1, then we get 2 as a result, and that's of course positive. But if we make one negative, for example, we take the vector 1 minus 1, that will give us a minus 2, and that's negative. So again, that Hessian here, HF of 0, 0, is indefinite. And therefore, 0, 0 is again a saddle point. And once more, let's have a look at the plot together. And you can see this is basically the simplified version of the example that we've seen before. So there's a saddle point again at the origin. Okay, that concludes the examples for today. There's going to be some more examples in the exercises, so be sure to have a look at those. And in the next videos, we'll then be concerned with the question of how we can recognize positive or negative definiteness more easily than through these tedious computations here. I'll see you then.